Now that we know a little more about the rate law, we can solve some problems. Here is a typical problem. We have a chemical reaction, 2NO plus O2 yields 2NO2. And we've been asked to determine the rate law using this experimental data. And then we're going to go ahead and calculate the rate law constant. So the first thing that we need to do is determine the general form of the initial rate law. And that would be rate is equal to the rate law constant times the concentration in molarity of NO raised to some power times the concentration of O2 raised to some power. Okay, we're going to look a little more at our experiments. We will see that they've talked about the concentration in moles per liter, which is code for molarity, so we can look at that. And this, another way to write that would be moles times second to the -1, and that's what we're accustomed to. So in order to determine the rate law, we need to find the orders of NO and O2. And I will look first for NO, and I am going to be looking at experimental trials where NO changes and O2 does not change. That allows me to see how changing the concentration of NO affects the rate. If both reactants were changing, I couldn't tell which one was affecting the rate. So I am going to compare trials 2 to trial 1. I'm going to put trial 2 on top so my numbers look good. So trial 2 will be compared to trial 1 to tell us how the rate law, at what order NO is. So then I just take the experimental data and put it into the rate law. And the experimental data for 2 is 0.0164 is equal to the rate law constant times the concentration of NO raised to some power times the concentration of O2 raised to some power. Not quite sure, but we always use M and N for our exponents. If I had more than 2 reactants, I would then go to O. Okay, and then trial 1, 0.0041 is equal to the rate law constant times our concentration of NO times our concentration of O2. We can see that K divided by K would give us 1, so that drops out. This drops out as well, and we are then left with 0.0164 divided by 0.0041 is equal to 4. And our other term is this divided by this is 2 raised to the n power. So we're looking for an exponent that raised to what power would give us 4? 2 raised to the second power will give us 4. So the order of NO is 2. Now to find the order of O2, I need to look at my experiment again, and I want to make sure that NO concentration doesn't change. So I can look to see how O2 concentration affects the rate. And this time I will choose trial 3 over trial 1. And the rate for trial 3 is 0.0082, and that's equal to the rate law constant. We now know that our order for NO is 2. Still don't know what the O2 order is. And then trial 1 is 0.0041 is equal to the rate law constant times the concentration of NO raised to the second power times the concentration of O2 raised to the nth power. This time these 2 terms drop out. 0.0082 divided by 0.0041 is 2 is equal to 0.040 divided by 0.20 is 2 raised to the nth power. N is equal to 1. So the rate law for this is the rate is equal to the rate law constant times NO raised to the second power and O2 raised to the first power. Remember, we never write ones because we're lazy. So now we're going to calculate the rate law constant, and again you use the experimental data. You know the rate law constant, and so you can choose any trial you would like. I am going to try trial 3. And so the rate for trial 3 is 0.0082 is equal to K, and then you pop in the values here. And O is 0.030 raised to the second power, and O2 is 0.040 raised to the first power. And that will give us, when we square this, multiply by that, and divide that into this, K is equal to 228. The big deal in the rate law constant is the unit. We discussed in a earlier lecture that the unit is the concentration, 1 minus the overall order, multiplied by the unit of time, which would be seconds, to the negative 1. The overall order here is 2 plus 1 is just 3. So this would be 1 minus 3, which is negative 2, times seconds to the negative 1. Now let's look at a problem that has more than 2 reactants. We have 3. We're going to follow the exact same procedure. We're going to find the order of this, then that, knowing that we have to use these different trials in order to isolate each one of the reactants. So to find the order of the bromate ion, I'm going to look for a set of data where only this changes while the other two stay the same, and that's going to be trial 2 compared to trial 1. Once again, I'm just going to put trial 2 on top because its numbers are larger, makes my math work out well. I recall that my initial rate law will have the general form rate is equal to this polyatomic ion raised to some experimentally determined value times this raised to an experimentally determined value times this. So I'm going to just take the values from experiment 2, trial 2, and put them in here. So 1.6 times 10 to the negative third is equal to the rate law constant times the value for the BrO3 minus 1 times the Br minus times hydrogen ion. I'm going to compare it to the rate here. So K divided by K drops out because it's 1, this is 1, and this is 1, which leaves us with this. So this value divided by this value is 2, is equal to 0.2 divided by 0.1, and is also 2 raised to the m value, the m exponent, m is equal to 1. So that is the order for this reactant. For the bromine ion, I'm going to look and see that experiment number, so now I want to see where the bromine changes but the others do not, and that would be experiment 2 compared to experiment, I'm sorry, experiment 3 to 2. So that's trial 3 compared to trial number 2. Popping in the values, given 3.2 times 10 to the negative third is equal to 0.20. We now know this is first order. This is 0.2. Those are our values for trial 3. Our values for trial 2. 1.6 times 10 to the negative third. So this, and this will fall out. 3.2 times 10 to the negative third divided by 1.6 times 10 to the negative third is 2, is equal to 2 raised to the nth power. N is also equal to 1. So we have the orders of 2 of our 3. And now I'm going to look for the order of the hydrogen ion concentration. And I will look around and see that experiment 4 has the first 2 reactants staying the same while the hydrogen ion changes, and experiment 1. So it will be trial 4 as compared to trial 1. 3.2 times 10 to the negative third is equal to K. We know that these 2 are first order. And number 1. So this divided by this is equal to 4. Oh, forgot the things that. In this case, the order for the hydrogen ion is 2. So our rate law is written as rate is equal to the rate law constant times the concentration of the reactants, this one to the first power, this one to the first power, and this one to the second power. Overall, the order is 4. Now we're going to find the rate law constant. So I will take any values, and so I will take these values and put it into the rate law. So the rate is 3.2 times 10 to the negative third is equal to the rate law constant. So it's 0.1 raised to the first power, 0.1 raised to the first power, and 0.2 raised to the second power. And when I square that, multiply it by this, and divide them into this, K is equal to 8. And remember that rate law constant unit is very important. It can be determined by the unit of molarity, 1 minus the overall order, which is 4, times the unit of time. And I'm going to go check, and my unit of time is in seconds. So that would be seconds to the minus 1. Simplifying that, K is equal to 8